Hello, and welcome to Luma's Laboratory. In this video, I'll be summarizing what I learned in week 4 of my first semester of my third year program. Check the description for more information. I didn't have time to animate this video fully, so please excuse the less interesting PowerPoint. Data analysis and machine learning. Neural networks form a collection of layers of nodes with connections between them. The connections are weighted. The value in a higher layer is a weighted sum of the previous one with some activation function for nonlinear outputs. Deep neural networks have hidden layers, allowing abstraction. Loss functions measure network performance, with a variety existing for different applications. Data is often pre-processed to allow better manipulation, including changing categorical data to a list of Boolean values. Hyperparameters modify the nature and nurture of the network and must be adjusted by a human or an algorithm. Numerical recipes. Interpolation allows one to find approximations for values of functions at points between those that are already known. Linear interpolation uses lines, Lagrange's polynomial uses one of high degree, and cubic uses many cubic polynomials. There is a logarithmic cost to finding the adjacent points and a differing cost to producing the model. Integration is done through splitting into intervals, interpolating within them, and integrating precisely then. Trapezoid rule uses linear interpolation. Simpson's and cubic rule use higher order interpolation. Adaptive integration uses varying interval sizes depending on smoothness. Simple techniques exist for improper or higher dimension integrals. Thermal physics. As discussed last time, the change in entropy is always greater than or equal to 0 for an isolated system. Expressing heat in terms of temperature and entropy, we get these central equations of thermodynamics. Here are 4 equations relating energy to temperature, pressure, volume, and entropy. By taking partial derivatives in different orders, we produce the following Maxwell relations, helpful for solving problems where some quantities are unknown. The quantities used in the finite differences are the natural variables for expressing the energy used. Lagrangian Dynamics. I will demonstrate one of many examples we covered this week. A pendulum is swinging in 3D space, theta describing the angle from vertical, phi describing the angle from a horizontal axis. We may write the kinetic and potential energies as such, with the Lagrangian being their difference. Using Lagrange's equations of motion, with each of the 2 variables we have 2 results. With theta, we uncover this result. Notice that when phi is not changing, we recover the original 2D pendulum equation. With phi, we uncover this result, which demonstrates the conservation of angular momentum about the vertical axis. Electromagnetism and relativity. By modifying the integral for the angular momentum of a complicated body, we may identify the moment of inertia tensor. It can equally be seen in the formula for rotational kinetic energy. The parallel axis theorem demonstrates the change in the inertia tensor as the rotation axis leaves the center of mass. Angular momentum is not necessarily parallel to angular velocity. If it is known to be parallel, we can express the inertia tensor as a scalar instead. We may identify the axes of rotation where angular momentum would be parallel by solving for the eigenvalues of the inertia tensor. Principles of quantum mechanics. We can consider observables with a continuous, rather than discrete, spectrum of possible eigenvalues and eigenstates. By considering the Hermitian nature of the operator, we can show that these eigenstates must still maintain orthogonality. The probabilities for the continuous spectrum are now described by a probability density function instead. An example of a continuous operator, besides the trivial position operator, is the momentum operator. This is the Schrödinger equation, describing the time evolution of quantum systems. The Hamiltonian operator has eigenstates for energy, expressed as such. For a system evolving with time, the coefficients transform in accordance with those eigenstates. Geometry. A differential K-form is the generalization of previously covered 1-forms. 1-forms can be combined using the wedge product to make a 2-form, which acts on pairs of vectors instead. Similarly, a k-form acts on k vectors. This wedge product is distributive, anti-commutative, and can apply to higher order forms as well. K-forms can be constructed from 1-forms, reordered nicely with anti-commutativity. The exterior derivative, previously converting functions to 1-forms, generalizes to producing k plus 1 forms. Two exterior derivatives produce 0, so forms with only 1 are useful and are called close or exact.